Welcome to all of you in this new video. In this video, I am going to discuss about the limitation or restriction on the use of Bernoulli equation. Uh, Actually, Bernoulli equation is one of the most widely used equation of fluid mechanics. However, it is also true that because of the simplicity of the equation, people usually tempt to use it even in those conditions in which Bernoulli equation is not valid. In this video, I am going to discuss about all those limitation and condition in which Bernoulli will be applicable and in those conditions in which Bernoulli will be not applicable. What happened in an interview? The interviewer was taking an interview with my friend. Now he asked, "Okay, tell me when Bernoulli equation is valid." My friend replied, "Okay, Bernoulli equation is valid for steady flow, incompressible fluid, and non-viscous fluid, etc., etc." Then the interviewer interrupted and he asked, "Okay, tell me whether Bernoulli equation is valid for gases or not." Now he got confused because he just said that it is valid for incompressible fluid where gases are compressible, whereas at the back of mind he was also thinking that he has solved many numerical problems in which he has applied Bernoulli equation even for gases. So he got confused. Similarly, I usually ask to juniors that, "Okay, tell me when Bernoulli equation is valid, whether for laminar flow or turbulent flow." Now every juniors get confused because it is a kind of tricky question. If you say that it is valid for laminar flow, then I can give several arguments which suggest that Bernoulli equation may not be valid in laminar flow. Similarly, if you say it is valid for turbulent flow, then again I can give several arguments which will suggest that Bernoulli equation may not be applicable in turbulent flow. So the actual answer is Bernoulli equation is valid in inviscid flow. It could be even laminar or turbulent. We will discuss at length in this video when Bernoulli equation will be applicable in laminar flow and when Bernoulli equation may be a good approximation in turbulent flow. We will discuss. But before I start this video, let me introduce myself. My name is Sandeep Kumar. I have done graduation in chemical engineering from IIT Roorkee. I also secured All India Rank 1 in GATE 2014. I have published couple of research papers in international journal and currently working as assistant manager at IOCL Haldia Refinery. But before I move, I would like to say that this video is going to be helpful to anyone who is from mechanical engineering department, chemical engineering department, civil engineering department, or anyone who is doing his graduation in physics or in fluid mechanics as a specialization. Okay. Now let us start our discussion. Now we know that this is the famous Bernoulli equation, which is essentially a statement of conservation of mechanical energy. Now what I mean by mechanical energy is the form of energy that can be converted to mechanical work completely. I mean 100% conversion will be possible if I use ideal mechanical device. For example, if I use ideal turbine, then I can convert all of the mechanical energy into mechanical work. Whereas for heat energy, I cannot convert heat energy to mechanical work 100%, even by using ideal machine. This is the famous second law of thermodynamics statement. So the mechanical energy are only those energy which can be converted into mechanical work 100% by using ideal mechanical device. Now kinetic energy, potential energy are a form of mechanical energy. Now for pressure, we know that a pump usually increases pressure of the fluid, and similarly a turbine extracts mechanical energy from the fluid and it reduces pressure. Therefore the pressure of a flowing fluid is also associated with mechanical energy, and it is usually called as flow energy. So Bernoulli equation usually tells that the flow energy, the sum of flow energy, kinetic energy and potential energy remains constant for a fluid subject to these following limitations. Okay. Now what are the limitation on Bernoulli equation? Now these limitations are listed here. The flow should be steady, flow should be incompressible, flow should be inviscid, Bernoulli equation will be valid along a streamline, or if flow is irrotational, then it can be valid even for across the streamline. We will discuss at length about when this will be valid only along a streamline and when it can be applied across the streamline. We will discuss. Similarly, there should not be any heat transfer, there should not be any shaft work. Now, how this limitation arises? This limitation arises when we derive Bernoulli equation. Now, Bernoulli equation can be derived by various possible way. It can be derived by using work energy theorem. Similarly, it can be derived by application of Newton's second law by simply force balances, or it can be also derived by approximation of Navier-Stokes equation. I am not going to discuss about the derivation because it is very simple, given in any book, you should just refer. But I am just going to discuss what are the what are the conditions in which this limitation will be valid. Now, if you look at the concept of physics by S.C. Verma, which is for class 11, there it is written that Bernoulli equation is valid for non-viscous fluid and incompressible liquid. Now, this is a very serious restriction. If you apply this restriction, then Bernoulli equation will become futile because none of the liquid which we find in real world is non-viscous. All of the liquid having some finite viscosity. Similarly, if you think on this incompressible liquid, then Bernoulli equation will be not valid for gases. But it is okay, this is correct, but reality is we can apply Bernoulli equation even for real fluid and and even for gases with only 1 or 2% error. So I am here to discuss about what are the condition or what are the situation in which Bernoulli equation will be a very good approximation. Okay, or what are the condition in which these limitation will be a very good approximation. So only those things I want to discuss. Okay, so let us first discuss about what will when the flow can be called as incompressible flow. Now, if fluid is liquid, then the flow of that liquid flow will be incompressible flow, no problem. Now, even for gases, if the velocity of the gases are less, or more specifically I should say that if the dynamic pressure, which is rho v square by 2, is not very large compared with the static pressure P, in that case what happened? Due to flow, the change of pressure will not be sufficient, and so there won't be any density change, sufficient density change. For example, see, suppose the gas is flowing in this nozzle. Now here area is high, so it means that velocity is less. Here area is less, it means velocity is high. In that case, what happened? Here pressure will be high and here pressure will be low. So since there is a pressure change because of this flow, and because of pressure change there should be density changes of gases. Now, what I mean to say that if these pressure changes is not very large, in that case density change will also not very large. In that case, we can consider that flow is incompressible flow. So there could be a possible incompressible flow of compressible fluid. I mean, there could be possible incompressible flow of gases. Now, what are those conditions in which that we can consider the flow is incompressible? Usually it is written in literature that when Mach number remain less than 0.3, in that case we can apply Bernoulli equation even for gases. For example, for atmospheric air, if flow speed remain below 100 meter per second, then in that case Mach number will remain less than 0.3, and in that case we apply Bernoulli equation. So we can see that this Bernoulli equation is valid up to very high velocity for even for gases, because in that case Mach number remains less than 0.3. So okay, we can apply Bernoulli equation with good approximation even for gases for low velocity. Now, since this dynamic pressure increases with as v square, so error will start increasing if the velocity start increasing. So for high Mach number, if we apply Bernoulli equation, then there will be a huge error. It won't be a very good approximation. So for high Mach number, we should use compressible form of Bernoulli equation. Okay. Now let us discuss about inviscid flow. Now, the apparent meaning of inviscid flow is it may be considered as the flow of a fluid which is having no viscosity. But this is not true, because flow of any fluid which is real will having some finite viscosity. So what authors referred when they say that the flow is inviscid, they usually refer that flow of a viscous fluid in a region of flow in which net viscous forces are negligible compared to pressure or inertial forces. Okay. Similarly, we will discuss what are the region in which the viscous forces remain very negligible, even though the fluid is having finite viscosity. Now, similarly, some of the author has written that the Bernoulli equation is valid for frictionless flow. Now, again, I am telling that they do not refer that there is no friction. There will be friction, but what happens for frictionless flow? There will be net friction will be zero. Net friction will be zero. So for frictionless flow, there will be friction still acts on fluid elements, and there may be significant viscous stresses, but what happens, these stresses cancel each other out and leaving no significant net viscous forces. Okay, so what are the region in which these viscous forces will become negligible? The region where if viscosity is very small or maybe zero, in that case viscous force will be zero. Similarly, if viscosity remains very high, in that case also, if this velocity gradient remains zero or the profile become flat, in that case also viscous force will become zero, and that flow may be considered as inviscid flow. So based on this discussion, let us try to figure out what are the region in which Bernoulli equation will be valid if flow is flowing over the surface, I mean for external flow as well as for internal flow. So this is the diagram for external flow, that is flow over a flat plate, and we can see that for a flow over a flat plate, usually there will be a boundary layer in which there will be velocity gradient, but beyond that boundary layer, that is outside the boundary layer, the profile of velocity will remain more or less constant. For example, here see, there will be velocity gradient inside the boundary layer, but outside the boundary layer velocity remains flat. So we can apply Bernoulli equation without any problem in this outer region, but we cannot apply Bernoulli equation inside the boundary layer. Okay. Similarly, we know that for flow over a flat plate, Bernoulli equation is defined as Reynolds number is defined as rho Vx by mu. So as length increases, this boundary layer convert from laminar to turbulent. So even for turbulent boundary layer, the flow velocity profile outside the boundary layer remains constant. So we can apply Bernoulli equation without any difficulty for outside the layer. Now, there will be velocity profile inside the boundary layer, and this velocity profile is usually maintained by shear stresses, and the work done by the shear stresses to maintain this velocity profile is usually converted into heat, and we know that heat is not a form of mechanical energy, so mechanical energy cannot remain constant for this boundary layer. And because of that reason, we can divide this flow field in two parts. One part where Bernoulli equation is valid, and the other part where Bernoulli equation is not valid. So if I want to examine the whole field, whole region, then we can separate these two regions and solve separately. So we can apply Bernoulli in this outer region, and the inside region we have to apply boundary layer equation, which is given in many fluid mechanics book. You can see. Okay. Now what I am telling is that it is possible that we can separate these two regions and solve for velocity and pressure profile separately, or if boundary layer remains very thin, in that case even simply Bernoulli equation will be a very good approximation. So let us figure out what are the conditions in which this boundary layer remains very thin. So we know that for boundary layer, the thickness of boundary layer can be determined by this formula. This is again can be derived by using boundary layer, Navier-Stokes in boundary layer. Similarly, for turbulent, boundary layer thickness can be given by this equation. So we can see that if Reynolds number goes high, then in that case boundary layer thickness will go very low. In that case Bernoulli will be a very good approximation. And when Reynolds number will be very high, when velocity of fluid is very high or the viscosity of fluid is very less. So you can also think that Reynolds number is inertial force by viscous forces. So if Reynolds number is very high, in that case viscous forces are small, and we can apply Bernoulli equation with very good approximation. Okay. Now let us discuss about flow, external flow, flow over a sphere. Now before directly I jump over to where Bernoulli equation is valid for this flow over a sphere, let us first discuss about the history of this analysis of this flow. Now what happened, if I take a very high Reynolds number, let's say 10 to the power 5, it's a very high Reynolds number. In that case I can think that this viscous forces are very negligible compared to inertial forces, and in that case we can think that this flow is inviscid flow. Now if I take inviscid flow, then usually for inviscid flow the flow is also irrotational. How? We will discuss in the next part of this video. So right now just think that inviscid flow is also irrotational, and for irrotational flow we can solve for a streamline mathematically, and after the solution, mathematical solution, we find a streamline look like this as shown in this figure. So for a high Reynolds number or for negligible viscous forces, a streamline look like this. Now if I took any two streamlines, then the mass flow rate should remain constant between any of these two streamlines. It suggests that if I took this streamline and this streamline, so as the fluid is moving in this direction, so area available for fluid flow is increasing. It suggests that the here velocity will be very less, whereas here at this point area available for fluid flow is very low, so velocity will be very high. And again at this point area available for fluid flow is very low, so very high, so velocity will be very low. So here velocity will be low, here velocity will be high, here velocity will be low. Okay. Now so the profile of velocity will be more or less symmetric. Now since velocity profile is more or less symmetric, so if I apply Bernoulli, so pressure profile will be also more or less symmetric. Now we suggest that the pressure at this point and pressure at this rear end and front end will be more or less same. So there won't be any drag force, because we know that inside the boundary layer there will be viscous forces, and viscous forces will be equal to mu du by dy, the velocity gradient times viscosity in times area. Now the viscous forces which apply inside the boundary layer, unseparated boundary layer, that viscous forces is called as skin friction, and the viscous forces which occur due to boundary layer separation, we will discuss just right now what is boundary layer separation. That viscous forces is called form friction flow or form drag. So since pressure at this point and pressure at that point remains same, then there will be no form drag. Similarly, since I have applied that this flow is inviscid flow, so there is no viscous forces, there is no boundary layer, so there is no skin friction or a skin drag. So it suggests that for inviscid flow there is no form drag as well as no skin drag, so no drag if fluid is flowing over a sphere. Now this is against the reality. Now this is usually referred as in fluid mechanics as D'Alembert paradox, because D'Alembert first found that there is a paradox if I consider at high Reynolds number that flow is inviscid. And because of that reason, earlier what happened, even mathematics was fully developed for fluid motion, we were mostly dependent on the experimental result, because the result of theoretical result was not matching with reality, and it remains unsolved. The D'Alembert paradox was found around 1770 or 50, I guess, and it remained this paradox remains unsolved till 1904. In 1904, Prandtl came with a theory of no slip condition. Okay. Now he said that even for very high Reynolds number, which is having very negligible viscous forces, there will be a layer of fluid flow where viscosity where friction forces will be very, very significant. Okay, so there will be a boundary layer. So Prandtl came with the theory of boundary layer, and if we use boundary layer theory, in that case what happened, there will be no slip condition, that fluid which is in directly contact with solid surface will be having zero velocity, and the fluid which is outside which is having distance with the solid will be having higher velocity. So there will be velocity gradient even for very high Reynolds number. Okay, so if I look at this, that there is a boundary layer against across the solid surface, then there will be skin friction because of velocity gradient or a skin ray. Now let us look at this sphere. So in that the velocity profile, how it will change if I will apply the concept of boundary layer. See here, velocity was very small, here velocity was very high. It means here pressure was very high, here pressure was very low. So fluid is was moving from this low pressure region to high pressure region, high pressure region to low pressure region, and that is called favorable pressure gradient. So fluid was moving from low velocity to high velocity. Fluid was accelerating or was moving in favorable pressure gradient, whereas here velocity was very small and here velocity was velocity was very high and here velocity was very low. In that case, fluid is deaccelerating and fluid is moving from low pressure region to high pressure region. So this is adverse pressure gradient. Okay, now what happened in boundary layer? Boundary layer, since the fluid is moving from this part to this part, and there is also a skin friction, or there will be a viscous forces inside the boundary layer, then what happened, the fluid which is having high velocity, its velocity start reducing at one point, its velocity becomes zero at this point, and there fluid will separate from this solid body and there will be flow separation. If you have understand what I am telling, it is okay. Otherwise you can also think that because of this momentum, fluid cannot take a sharp turn in this way and fluid will go pass in this direction. Okay, and because of that there will be flow separation. Now this flow separation concept is very clearly explained in one of the video by a professor of Cambridge University. I will give a link in the description of this video. But anyway, when fluid will separate in the rear part of the sphere, so what will happen? There will be a region of very low pressure, and because of this low pressure, here pressure is low, here pressure is high, there will be a foam drag which will be applicable on this sphere. So there will be a skin drag as well as foam drag even for very high Reynolds number flow. Okay, now the region, this separated region, the fluid is usually remain in the form of vortices or eddies, and this region is called wake. So in this wake, fluid will remain always in constant motion, and because of this constant motion, why this constant motion? Because of the shear stresses between this wake and the separated current. So these shear stresses, what it does, it converts mechanical energy into again heat energy, and because of this there will be huge mechanical energy loss. So again Bernoulli equation will not be valid in this wake region. So for flow over external flow, we can think that Bernoulli equation is not valid inside the boundary layer as well as inside the wake region. Okay, so to understand fully or to fully solve this problem, we have to apply Bernoulli equation outside the region, outside the boundary layer and wake region, and we have to solve boundary layer equation for this laminar boundary layer as well as turbulent boundary layer as well as wake flow. Okay, enough for external flow. Now let us discuss about internal flow. Now for internal flow, you know that the velocity profile look like this. And if velocity profile look like this, it suggests that for fully developed flow, the whole region is filled by boundary layer. Okay. Similarly, for turbulent flow, the whole region is filled by boundary layer. And so Bernoulli equation is not valid for fully developed flow. And to to make Bernoulli equation valid, we need to modify the equation, and we need to consider the head losses because of this viscous shear stresses, as well as we need to consider the kinetic energy correction factor, because the velocity profile is not flat and the velocity is having radial variation. So if we apply these two restrictions, then Bernoulli equation will look like this, and this head losses is usually given by this formula, or Hagen-Pauli equation for laminar flow. We all know that. Okay. Now what about developing flow? Now for developing flow, we can see that the velocity profile remains flat, more or less flat, for core flow region, whereas for boundary flow there will be a velocity gradient. So okay, we can apply Bernoulli equation for developing flow inside the core region, not inside the boundary layer. Okay, because there is no velocity gradient, and in that case we can consider the inside the of the core region flow is inviscid flow. However, for laminar flow, due to mixing, the flow usually develops at very small length, so the chances of Bernoulli equation applicability will remain very small. So if I apply Bernoulli equation for long pipe, there will be huge error. If I apply Bernoulli equation for very small pipe, then there is chances that flow has not been fully developed and Bernoulli equation does not possess a large or huge error. And that's why we have to figure out that what are the entry length, or what are the length required for flow to be fully developed. So if the flow is laminar, we know that the entry length is given by this formula, and suppose if Reynolds number is 20, then it suggests that only one diameter length will be able to develop the flow in fully developed region, and because of that reason, for very low Reynolds number we cannot apply Bernoulli equation, because at very small length flow will be fully developed. But if flow is having very high Reynolds number, in that case what happen? In that case, hydrodynamic entry length will be 115 times the diameter. So we can apply Bernoulli equation for, let's say, 20 diameter up to 30 diameter. Okay. So similarly, for turbulent region, we have just seen that due to mixing, flow usually develop at very small length, and because of that reason, this turbulent entry length is given by this formula. And in most of the practical engineering interest, turbulent boundary layer entry length is entry length means length required for flow to be fully developed is given by this formula. So we can apply Bernoulli equation for inside the flow for very small length of pipe, okay, or when Reynolds number remains very high. Okay, if you have to understand this concept thoroughly, okay, otherwise you can also think that if pressure losses remain very small, in that case my Bernoulli equation approximation will be very good, and in that way it suggests that if length remains small, or diameter goes very high, or velocity goes very low, in that case Bernoulli equation will be applicable for flow inside a pipe. So in Sengel chapter 5 it is written that frictional effects are negligible for short flow section with large cross section, especially at low flow velocity. Similarly, frictional effects are usually significant in large and narrow flow passages in the wake region downstream of an object. Okay, and that's why you may have seen that many numerical examples, the flow pipe is look like this. In that case, we apply Bernoulli equation because the length of the pipe is very small and the entry area and the bended are very are not sharp bend and sharp entry. Okay. Now let us think about this was all about the flow inside a pipe which is having very cross sectional area same, and let us think about when the flow is having increasing cross sectional area or decreasing cross sectional area. In that case, what will happen, that if flow is going through a sudden expansion, then there will be flow separation, and again there will be frictional losses, so Bernoulli equation is not valid. Similarly here Bernoulli equation is not valid. Now let us see about a a smooth converging and diverging section. Now if you take a smooth diverging section, what happens? The flow velocity is decreasing because cross sectional area is increasing, and in that case fluid is basically moving from high velocity to low velocity region, so fluid is deaccelerating. Or we can also say that fluid is moving from low pressure region to high pressure region, so fluid is moving in adverse pressure gradient. And we have just shown that whenever a fluid is moving from low pressure region to high pressure region, that is against adverse pressure gradient, there will be chances of flow separation. So if there is a smooth converging section, we cannot apply Bernoulli equation because of flow separation. Now here in this diagram, which I have taken from McCabe and Smith, I am explaining flow separation in another way. Suppose if I take two flow stream, one is AA and another is BB. If I take these two flow stream and if I take cross sectional area at this point and cross sectional area at this point, I mean for this S and this another point. Now the pressure change from this point to this point will remain same for both BB and AA streamline, because pressure at the one cross sectional area will remain more or less same. Similarly for another cross sectional area, pressure remains same. So pressure changes from going from this point to this point will be same for BB as well as from A. So the change in velocity should also same. And we know that since A is very close to solid body, so the velocity of A is less compared to velocity of BB. So if change in velocity for BB as well as change in velocity for A is same, it suggests that there will be a point in which at which the velocity of A will become 0, whereas the upper flow stream, the velocity will remain still finite, because it has earlier higher velocity and change is same for both these streams. So there will be finite velocity for BB. So what it suggests that the flow near the solid boundary will loses its velocity, whereas the flow outside or the far apart from the solid boundary will having velocity still. So what will happen? Due to this zero velocity, the fluid from this part will start moving in this direction, and there will be fluid velocity in reverse direction. So fluid is moving from this part to this part in this direction, and the fluid is moving from this part to this part in this direction. And there will be a point where velocity is 0. At that point is called flow separation point. So since there is less or 0 velocity at this point, so fluid will have only one possibility, that fluid will move in this direction. Okay. Now again I am telling that this flow separation concept is very clearly explained in a video. I will give a link. So whatever the reason is, whenever a fluid deaccelerate or the fluid is moving in adverse pressure gradient, there will be flow separation. In flow separation, boundary layer thickness goes very high, and in that region Bernoulli equation is not valid. But what about converging section? For converging section, because velocity is increasing or fluid is moving in favorable pressure gradient, there won't be any flow separation. Boundary layer remains very thin, and we can apply Bernoulli equation for small nozzle without any difficulty. Okay. Now you might have seen that we have applied Bernoulli equation for flow meter velocity derivation, and the reason is why we were able to apply Bernoulli equation in venturimeter, because flow was moving in converging section, so we can apply Bernoulli equation in venturimeter. Now for orifice meter, there will be a flow separation, but what we use to take the tapping at just upstream of the orifice as well as just downstream of the orifice. So from this part to this part, we can think that the change in pressure is just because of change in velocity. Only this much length has not done much pressure loss. So if I apply Bernoulli equation at this point to this point, then that will be a fairly good approximation, and by applying this Bernoulli equation up to this point, we can solve for velocity. But if I want to know that what is the pressure loss due to this orifice, then what you have to do is you have to apply Bernoulli equation. You have to apply for energy equation at this point as well as at this point, where flow is again fully developed. So in that case, we will be able to account the losses due to wake formation in this region. Okay. Now again, this concept is very clearly mentioned in a video by Cambridge University professor. I will give link inside in the description. However, if you want to take even more accurate result, so in that case we have defined discharge coefficient. You may see in any fluid mechanics book. Okay. Now enough about this inviscid flow. Now let us now discuss about the other assumption. We suggest that there will be no shaft work, and again this is required because we have already told that Bernoulli is essentially a mechanical energy conservation equation. So it means that if you are not taking out the energy, or you are not providing energy from outside. So if I am using a pump, then I am providing energy from the outside or by the pump. Similarly, if I am using a turbine, then I am extracting the energy of the fluid. So Bernoulli equation should not be valid if I am using shaft work. How? Okay. Similarly, there is another requirement is there should be negligible heat transfer. Now, if there will be heat transfer, I have three problems with Bernoulli equation. The one is that due to heat transfer, temperature will change, and when temperature changes, density of gases changes even for very low speed. So Bernoulli equation will not valid. Similarly, Bernoulli is again essentially mechanical energy conservation, so we should not extract energy as a form of heat, or we should not provide energy as a heat, because even if I heat the fluid, some of the heat energy may be converted into mechanical energy. So this should not be valid. And the third part is usually when there will be uneven heat transfer, then what happens, the fluid which get hot will get density low, and the fluid which get less heat will be having high density, and it may create circulation between the low density fluid and high density fluid. So it may create rotational fluid, so the fluid will not remain irrotational. So that's why we should not apply Bernoulli equation if there is a heat transfer. Now, based on all these conditions, I can fairly say that Bernoulli equation for this aeroplane flow will be valid in this region as well as this region. But in this here not valid because of wake formation. Here not valid because there is boundary layer. Similarly, not valid boundary layer. Similarly, if there is a propeller, we cannot apply Bernoulli equation because it will impart energy to the fluid. So if I would like to apply Bernoulli at this point to this point, then it will give a bad result. But we can apply definitely Bernoulli equation from this point to this point, and similarly we can apply Bernoulli from this point to this point. Of course, the Bernoulli constant will be different. Inside this region, we cannot apply Bernoulli because there won't be any steady flow. The fluid is having very large fluctuation of velocity and large breakdown of streamline, so we cannot apply Bernoulli equation inside this region. Similarly, for this chimney, we can apply Bernoulli here, but not in this region. This is boundary layer region. Similarly, we can apply Bernoulli here because this is inside the core region, not here, not here. But again, since here we are supplying heat energy, so we cannot apply Bernoulli equation in this region. We can apply Bernoulli at this point to this point, or this point to this point, and the constant Bernoulli constant will be different for these two. Okay. Similarly, we cannot apply Bernoulli here. This is a very long pipe, we cannot apply. Here is heating, cannot apply. Here is shaft work, no, not applicable. Here is a globe wall, and it is like a sudden expansion, not applicable. And again, in the wake and boundary layer region, Bernoulli equation is not applicable. Okay. Now there are other condition also, limitation also, that is a steady flow. flow along a streamline and irrotational flow. I will discuss in detail about irrotational flow. This is very interesting concept, and I will show that if I say irrotational flow, it is equivalent to say that the flow is inviscid, and we can apply Bernoulli equation, and we will also figure out that irrotational flow can also be called as potential flow, and we will also discuss about in depth that what are the conditions in which Bernoulli equation will be valid for turbulent flow with fairly good approximation, and what are the conditions in which Bernoulli equation is not valid for laminar flow. We have discussed a little bit. We will detail in the next part. Whatever I have said, I have taken from various books by Sengel, by McEwen Smith, by Fox McDonald, by Frank M. White, Bruce R. Munson, and I have also discussed some of the topics with Professor John M. Simbala, who is the co-author of the book Fluid Mechanics Fundamental and Application, and the Concept of Physics as well. Thanks for watching.